Hi, everybody. So I wanted to actually just record a video going over the pre-lab information for Module 4, Task 2. This way, you'll be able to just come to lab and get right to work without having to listen to me. And really, the big reason for that is because you're going to have to do a ton of titrations. You're titrating all of the Green River samples plus a standard, which we'll talk about. And you're going to need to do each of those at least 3 times. And so you're looking at doing somewhere in the neighborhood of probably 20 individual titrations when you come in for your lab. Sounds like a lot, but it's really doable. You've been through the process at this point. You've done the titrations. You know what to do. And the good news is that you don't have to mix up that KiO3 solution like you did for the standardization. So you'll literally be able to come in, pour the samples into a beaker, and just start titrating, just start going to it. And so let's talk about the lab itself a little bit. And so, okay, so here we are at task 2. So remember, the whole idea last week was to find your standardized concentration of your thiosulfate solution. Now that we know that precise concentration, we're ready to use that to titrate the Green River samples and find the actual dissolved oxygen content. This is taken right out of your methods. And so as I mentioned briefly just a couple minutes ago, all of the samples at this point have been treated with the solutions that you used last week in order to get the KiO3 solution ready. And so that solution 1's been added in there. The divalent manganese has been added in there. And so everything's been done. And so you're essentially starting from, let's see if I can find it in here. So just like when you did your titrations last week, you're starting from step 3 in what you did last week. So you're going to fill your burette with your thiosulfate solution and do everything that we did last week. Put a little bit in your burette, rinse it out, coat the inside of the burette with your thiosulfate solution, fill your burette up a little bit above the 0, open it up so that the tip fills, all that preparation of the burette that you did last week. Do that, get your thiosulfate solution into the burette. But then you'll be starting from just flat out titrating. The samples are all set to go. You will pour, I think in the procedure, it does say for you to put, I think 30 milliliters of each sample into your beakers. You'll want to be pretty precise with that. And so you use tools in order to measure that 30 milliliters very precisely. Then you're just going to start titrating. Now let's take a look at how you're going to actually do the calculations for this. And so remember that this is the basic reaction that we're running. And so everything's been done in the samples to convert the O2, sorry about that, over to the I2. And so remember that the thiosulfate then reacts with that. And the starch indicator will turn blue with the I2 in there. And then we'll turn clear once all the I2 is actually gone. So then at that point, so at your end point of the titration, when everything turns clear, you're going to have a titrated volume. And so again, literally just the volume from your burette. You're going to run through the titration. You're going to have a volume at which the sample turns completely clear. That's your titrated amount. That's how much of the S2O3 that you used. You then multiply that by your standardized molarity. So the molarity that you found of your solution last week. And so we're multiplying our liters of the S2O3 by the molarity of the S2O3. That tells us then, if we stop right here, that tells us how many moles of S2O3 we had to have used in order to get to the endpoint of our titration. We can then use all the stoichiometric ratios from the equations to relate that back to the moles of O2. And so these are just the straight up equations from your lab manual. Those of you in my section, we went through these and we looked at these as part of our pre-lab last week. And so what this does, and so backtrack these if you need to, go back and look at your manual, look at these equations. But what this gets us to is our moles of O2. So this tells us how many moles of O2 had to have been in the beaker. So that's actually sitting down in your beaker That tells you how many moles of O2 were in there initially, were in the river sample initially. So again, you take your titrated volume, how many liters, you're going to measure in milliliters, convert to liters. So how many liters did it take you to get to your endpoint? Multiply that by the standardized molarity that you found last week, somewhere a little bit under 0.004. Most of them were around 0.0035, somewhere in that range. But whatever yours actually was from your solution, so you're going to multiply that. And then divide by 2 and divide by 2 again. And that tells us how many moles of O2 were in the initial river sample. And we know that we used 30 milliliters. So we know how many moles there were within 30 milliliters of the sample that we started with. And so you're going to take that moles that you calculated in the previous calculation and divide that by 0.03 liters. That gets us to molarity. Now, remember that we always do, or that we report dissolved oxygen in ppm. We don't actually report dissolved oxygen in molarity. So we need to convert our molarity over to a ppm. And so from your molarity of O2, you're going to then multiply by the molar mass of O2, and then multiply by 1,000 to convert to milligrams, because another way to express ppm is milligrams per liter. And so that's all I'm doing in this conversion here is I'm going from moles per liter and converting that to milligrams per liter, which is equal to ppm O2. So once you find your molarity from the previous calculation, just do this with it. Multiply it by 31.998, multiply by 1,000, and that will finally get us to the ppm level of O2 within our samples.